Welcome back to High Performance Computing, Advanced Scientific Computing. We have our lecture 3, Parallelization Fundamentals, and the second part of it. In the first part, we clarified more in deep details domain decomposition as a sort of terminology in HPC, which can stand for lots of things. Data parallelism, functional parallelism will have an influence on this as well. We had the example of different codes working on different areas, let's say atmospheric level and surface level, which would be much more functional modeling. They solve the physics differently, but interact with each other to really give a real big picture. And in similar ways, we have seen then the interesting stencil methods that although they basically compute for every tile, for every grid part, always the same, right? It was basically the idea that we had with the Jacobi, with the heat in the room, for instance, or any other physics you want to do in this area, the weather prediction, for instance, they would, of course, have then in this particular areas of the grid the same code to execute, but with different data. Hence, same program, multiple data. And this is usually a big paradigm. And we have also seen, in order to do so and simulate something in parallel, the way why we want to do it, to give a big picture, a simulation over time, it is necessary that we do communication exchange, right? So that we basically exchange this parameter and from time step to time step inform what was happening in the last time step and involving the neighbors. So all in all, the last lecture part really was to stimulate a little bit to you that the world is not all completely Cartesian alone, that everything is nice and shiny, that we have one round computing, everything is done. We rather see a numerical process really, so iteratively going to the solution. So there's also some approximations involved, hence why we cannot predict the weather in, let's say, 20 days with an accuracy of 99%. We can't do that because there's numerical instability after 6 days. So there will be, the simulation a little bit, wiggly. You know that by now from all your apps that you download and predict weather. No one can predict the weather, let's say in 50 days to a degree of 99%, because we want to have real observations integrated. And we have a certain amount of, physics that really can work that far, but it works pretty well. We know that already for a couple of days because, this topic has been advanced. But I don't want to discuss all again what we had, of course, in lecture 3, part 1, but I would encourage you, in order to understand some elements we will talk in now in the second part, it is maybe good to have the terminology again that we established a little bit with domain decomposition, iterative methods, stencil methods. Over time is really the point here, which will have then also an influence how much we can do with high performance computing. Memory is a limiting factor. Computing, we maybe not have infinite amount of processors. So there are lots of elements into this parallelization. That's why we call it parallelism fundamentals, which you need to know in order to tackle a problem really in parallel. Now, what I want to do now in this part is not to do a kind of formula by formula thing and go to all the different terms, theories and theorems. We have even some laws in HPC, Gustafson's laws, Amdahl's law, and to some extent even Moore's law, although it's bigger, bolder, whole computing. Still, this is more a lecture of giving you now a little bit of connection to, again, the parallelization scheme of things, the performance measure, what it really means to be high performant. And that's why we need some formulas, but not for the sake of it. Just to understand that, of course, adding more and more processors is sometimes limited. And there are some established words we have to talk about when we talk about high performance computing, which I not really have talked about so much. And this is scaling. Scaling is a term which is very well defined basically in HPC. There are 2 variants of it, weak scaling, strong scaling, for instance. But in a way, that's what we want to do in high performance computing. Of course, we want to scale up our problem most linearly if we can, which means more and more computing means to more and more results. And we will talk about this now in the lecture. So this will be now, again, some, ideas where we can motivate the whole problem. That parallelization is, of course, now not only the idea of having more speed to it, we also want to add more detail to it, what you learned in the ocean part in the last part of lecture, but you can also make the connection here if you think about a tree or basically a sort of terrain that you want to simulate, plants that we simulate in 3D. This is virtual reality. Here's an example of a train that we burn. Of course, this is quite nice because we don't do it in physics. On a reality, we do it in virtual reality using high performance computing. We can test out different materials, how much it burns down the train, how quick, how fast. There are lots of studies you can do with this, very basic high performance computing, and you can put in more and more reality and more, elements of granularity in it to the train on compartment level, or let's say on a really, let's say several parts in it, like the roof with some very specific materials, etc., etc. So, which means there are lots of capabilities in using HPCs for problems. And right now, everybody of you is aware that deep learning networks and using workflows, then, which is a bit shown here as well, shows you then the whole picture, perhaps, of a real problem that we face in the real world. But HPC can really nicely help to enable these capabilities to simulate this, and which then requires us really to go in parallel, because one microchip or one chip is not enough, right? Hence, we need more of those together, and which was also then the idea of this Moore's law that you remember here a little bit on the left. I think, that essentially the number of transistors that you have on these chips is doubling every couple of years, 2 years, which was then sort of an interesting growth factor, which was stopping at some point in time when we said, well, multi-core is nice, high single set performance is nice, but the chips get too hot. So unfortunately, we cannot put more and more transistors, more and more cores on the chip. It would be getting too hot. Hence, there was then suddenly the GPU to the rescue and said, okay, we don't do maybe this cutting edge cores, but for some problems like we have seen successfully in AI, it actually makes sense to do moderate, processors and many of these chips, many on these chips. And you see here the latest evolution of Grace Hopper cards. This goes back to a long tradition. We will have GPUs in lecture 5, so I will not talk too much about it. But this was really growing from very, let's say, interesting architectures in the Kepler, Volta, up to Ampere, which already then featured tensor cores, very optimized cores for deep learning. We will talk about it. To now Grace Hopper cards, where you have even here this interesting NVIDIA NVLink, and I'm not paid by NVIDIA, but NVIDIA has quite a market share and interesting technology, where you have the CPU plus GPU coherent model of the memory, which was sort of a limiting factor a long time for GPU computing. Some of you know that used also my courses in the past or looked on YouTube. Here we're talking now about interesting developments that the main memory of the CPU and the GPU is quite, let's say, having the same memory model, helping then really with the throughput of the application. So these are terms which are, quite established. You should know, like multi-core, many-core. I think this is getting also mainstream today. Some actually say to many cores these days also accelerators. Hence, our lecture 5 will be also called accelerators in GPUs. Accelerators is a broader term. We have to talk about it. But by now, you also can imagine the reasons for parallelization. I mean, there are two major reasons, which means that usually one core is not enough to do the required task. Let's say burn a train and all the material details that we have seen in a certain amount of time. So let's say over the duration where the train is fully burned. On the other hand, we have seen then what I thought could bring across very nicely in the Earth system research. You would have lots of memory variables. For a single system, this would be too much to do, right? Your laptop will be out of memory very quickly of storing everything, which is, in this Earth system elements from atmosphere to down to the land surface and so on. Hence, these are the ideas of dual parallelization methods like we have discussed with SPMD, or you do the MPMD, as we also have already introduced as terms. There are different ways, but want to achieve one thing, usually making it work if there's not enough memory, or making it faster, which we then establish with something we call the speed up term. The speed up term here is a good example for. I mean, you basically would have, again, some, let's say, task, whatever it is, right? And now we abstract a bit. I'm sorry for this, but this has been now a bit more abstract and we go into some formulas. But in the end, we talk about certain tasks that in this time can be done. And the work that has to be done is here the amount of 12. And you have just one worker, he just have to do this sequentially over time. Now, if you come to the situation where you say it's nicely parallelizable, nicely in the sense of, you know, the time step before is not depending, the time step now is not depending on the one before, then you can maybe also do something like this, right? You put them all together in parallel, yeah, with this condition. And then you have a speed up of a certain amount, a speed of n, if you say you have 3 workers, then you can compute essentially a speed up, very simplicity wise. I mean, this is a very trivial example of saying, well, we have this t would be, let's say, the 12 time steps that I need to do the work usually, but with 3 workers, we can go down to 4 time steps to do this work. And then you can, of course, balance. More workers means, you know, less time steps. But is it really possible? Does it make sense? And so on is another question. So we have to go in much more detail to understand speed up and to understand then also scaling in principle what we do here to more and more processes. It gives us also the opportunity to think about another term which is very important in HPC because it burns cycle for nothing. It leaves it essentially not used. And this is a thing. And it is, however, very natural to have this. If you compute physics formulas, that all have always the same ideal picture that you saw in this one, so that each chunk of work takes the same amount of time. Although there might be very different and very similar physics, there might be different data, takes longer, one task is shorter, you see that here and here, which brings us to the fact that when we have this work over these different processes, they should also, let's say, have an ideal resource usage of 100%, which is probably not reachable, but use the resources to the most possible degree. Because when you allocate it, you have seen this in the scheduling work the last couple of lectures, it's allocated to you. No one else is using the processor. So hence, when you use a processor, you want to get it active. You don't want to have idle time, as it is also called, right? Here, the unused resources, it's idle. No one is using it. No one else can use it because you have allocated it for your job script. Hence, the work that you do should be also ideally balanced. And this is really a problem. Hence, load imbalance term, which is not at all to achieve always in these applications. So you have to think about very carefully about how you crunch again a big problem into smaller pieces, because you don't want to have the situation that one worker is finished in a minute while the other worker is still requiring 1 hour. So hence, in other words, maybe not at all always, it's always the same amount of work like suggested here that makes the best domain decomposition in this sense and the mapping to the processes. So you get more and more the idea that parallel performance to achieve is not the simplest. You see a very good example, you know by now, from MPI ranks, from the MPI, what we discussed the last time. I will not repeat this. 32 processors have some work to do. And what we identify here is quite a load imbalancing scheme. So first of all, everyone here is already quite imbalanced. They compute something. What it computes is not important for us. Important is for us that there are lots of idle resources. And why is that the case? Because you see that on rank 0, that essentially, even if all the processes are actually done after 20 seconds, the whole job space, let's say the resources you have, are still occupied with your job, right? Your MPI rank 0, probably doing a master worker scheme. So using rank 0 as a master, which is common sometimes, getting all the results from these ones, is doing now the, let's say, maximum of an area, whatever it is. And the overall compute time is 38 seconds. Now, simple, explanation of this. But there might be different issues that this now leads to a fact where the administrator will call you of the HPC system and say, well, you don't really use allocations very much. You allocate your job and it's actually needing, of course, this allocation, at least for one task, MPI rank 0. Thank you very much. Congratulations. But all others are actually absolutely in idle. And these are elements we want to avoid. right? So what you see here is not an ideal situation. This has lots of problems that can lead to it. One is, synchronizations, which are maybe unnecessary, this MPI wait all that we are from non-balancing, basically the communication MPI, which was non-blocking. So then this could all lead to load imbalance from the data perspective as well, from the load perspective. And sometimes you have even serial execution limits. Let's think about that. Maybe some of the things should be going then to IO, and someone has not done parallel IO, that you also will know by now from lecture 2. All processes will write in the file at the same time. Someone has done maybe a serial IO and saying rank 0 is the only one writing to file, and the file system is just waiting and taking time. So serial execution limits could be also the case. Now thinking about that, this is now bringing us to a very interesting situation where you think about, okay, not all in the world is Cartesian, right? Some things has to do with distances, for instance. And I think the tree codes here for n-body simulation is a very good idea where the short range interactions are differently computed from long range interactions. And with this, if you model this a little bit in a particle space, for instance, like this n-body problems here, you see it could be some specific particles that you want to accelerate. Here you see a sort of short idea of a laser cannon. It was one idea to solve cancer in the past. So, or at least, help with cancer. The key message to take away is that you interact between different force fields and different, let's say, equations of physics with other particles. And by doing so, you have lots of particles to cover in the space you see here. And the more particles you add, the more to compute. Hence, in some areas, maybe for long range interaction, for instance, and you have to define what long range means, right? It might be something, certain distance from the one you compute right now. You want to switch to a more, let's say, tree-wise setup that you see a little bit here in this particular element. And this is just showing you as an example, and we have no time to go into this very much in detail, that this particular code that we use here for some examples is sort of a tree code. So it's not really Cartesian, right, in a way. So here we have different physics steering now the idea how we do also the domain decomposition more effectively. And this is a Pepsi tree code, which see with this tree approach can also scale quite highly, which we probably would not the case if we don't have the tree code. Hence, now this is now the point making it now as an influential factor in this so-called scalability. And with this, you also see that high performance, domain decomposition, scalable applications, this is all connected, right? You cannot see and make one error in the domain decomposition method and then think, it can still scale very well. And even if it does, maybe it has load imbalance, and then the administrators are not happy. So there's a lot of interconnection work that needs to be done. And let's look a little bit on this kind of speed up more in detail, and also maybe a little bit more in terms of theoretical wording and formulas, but keep some, let's say, important terminology into our mind. So one of the simple ideas is speed up, where you think, okay, 2 instead of 1 processes. Do I really improve on 50% in accuracy, or do I really improve on 50% of speed up for the simulations? So these are still questions which needs to be tackled. And in many cases, if not in all, there are limits, right? You have, of course, an ideal linear scaling that you see nicely in this plot here. It would be the more cores I have, the more speed up I have. But the reality shows us these plots that you see here, there's a sort of tail off. And this is an area where it's now get into a problem domain, in a sense of saying we lose the parallel efficiency. Today, you would even say the more compute you put, the more energy you waste, right? So there's also a sort of energy factor to it, and say, well, with green energy, it might be not so dramatically, but in generally, if you have green energy to be wasted and the speed up is getting less and less, so the tail off could be very dramatic up to, stagnating, then it doesn't really make sense to apply more cores. In other words, the parallelization has its limits, right? And we see that in many of the application examples. Hence, we have some sort of metrics for it. where you can show this explicitly, which is, of course, our goal to be near linear performance, but you have different ways how you combat this, how you can make it better. One idea that you see here in this example from our clustering algorithm is, for instance, that you don't use just MPI, you use also shared memory, right? You see with MPI, at some point in time, we tail off quite early, but, and this is different data sets for clustering. We should here DS1 and DS2, but that doesn't matter so much. But you see this hybrid, which stands for MPI plus OpenMP, something you will learn in lecture 4, we can keep close to linear performance still and don't have a major tail off here. But this is something what you need to analyze, that you want to show by the number of cores when you scale up with your application. Hence, we have these two metrics, strong scaling and weak scaling. And now I really want to have your attention, because this is a common question and answer session with my students all the time. So the difference for that seems to be still for many a bit an issue to understand. And I understand that maybe it's going already into the details of HPC, what you want to do with it. But the scalability metric, maybe from strong scaling to start with this, it's sort of the really intuitive way. You would say, what parallelization benefits I have, right? So you see this here in green. So you have a total problem size you want to have, and it will always be like that. All what you do is you increase the number of processors working on it, right? The same work, more people. Think about eating a pizza with 2 students, 6 students, 12 students, 20 students, how much pizza is left for you? So this is basically the idea. And this is what we want to show then in terms of limits, that at some point in time, that the analogy with a pizza suggests, right? When you have 100 students in a small pizza, there's not much left for you to do as processor. So why you do this? And this is the scalability metric of strong scaling. I have some example later, just to contrast it now. So weak scaling, right? So weak scaling is now different. And the key difference is to think that the problem size increases with the rate of processes. And this is really important to understand. I know for some it's very trivial, but somehow my students always come back to me, Q&A, what is now the difference? The problem size increases in weak scaling, in strong scaling, it remains every time the same problem. You do different runs with different number of processes. Yes, in strong scaling. In weak scaling, you don't do just more processes, you also increase the problem size of the applications, 1 million particles, 2 million particles, but also more processes. So in a sense, what we want to see is a bit the sweet spot of keeping the work per processor the same. And I think some students really in discussions reveal that what it is possible to do, right? This strong scaling, you get the parallelization benefits of having more processors for one problem. But in a way, with weak scaling of an application, which is of course our idea, why we do this, we have an application, we want to see what is it possible to do. We keep the work per processor the same, we scale up more processors, more work, more processors. So we keep the work, keep them busy and see what's possible. And in a way, you could see it's similar like the idea of having more and more detailed of the application there. And this is also the way towards thinking, getting better simulations, towards reality, more granularity, and so on. So let's have some kind of small formulas before we go again to some plots and so on. So when we say strong scaling, again, we have this kind of fixed size problem, right? This is now this TFS, which is basically coming out of the serial part of an application plus a parallel part. The serial part could be, for instance, the initialization. You have seen MPI init starts at some point in the source code. Maybe there are elements before. Could be the kind of idea to first that the scheduler actually have to put all the MPI executables on all the different nodes allocated and then runs the application. So there's certain serial overhead always in an application. The P part is, of course, then the nice part that we see in the MPI program that we actually parallelize, right? Ping and Pong, we have 2 processors. That's something what we have divided by 2. and say, okay, but it was not really a speed up in that example. But then when we think about two processes having the same work, right, that we want to do, we can apply now here 4 processes, maybe 8 processes. If there's a parallelizable array that we have seen, for instance, we want to crunch down the time of having the max of an array. This is nicely parallelizable. So let's do this. Still, there was a serial part that remained a bit, if you remember, with the max global of the local part. So someone has to compute this. And this is not to be parallelized. We need the output out of the parallel entities, the local from the arrays. Hence, this is something where there are also, of course, at some point limits, and it was also leading us here a little bit to an interesting fact that we have that the parallelization of, let's say, of a program, really of a time for an application is often in its serial parts, and hence we have a law for it later. But here, think about again, when we now want to contrast it against weak scaling later, the work stays constant. And we have more and more processors for the parallelizable part. That doesn't help us, however, for the serial part. And here the goal is really of the parallelization, minimize the solution time, right? Just speed up, pure speed up, something that I can, crunch down smaller, just do it. And here are some examples of strong scaling. And you think about each of plot is in itself, right? So you see the number of cores we actually execute to the right. And then you see essentially the different runs that we've done with, different factors in terms of the application size. But this means still for each of the problems we have, the solution size stays, right? And then we see the tail off coming up every now and then when we see here number of cores 4,000, for some of the problems 64,000. Note the exponential scale here. So this is something which is important. And this is a strong scaling example. It's a bit older example, but it captures still the essence. And you basically see here different use cases, really, where you have the different use case on the top with homogeneous particle distribution, right, which scales, let's say, quite good. And then you have the inhomogeneous particle distributions, bottom, different use case, where you then have, let's say, as you see here, the space is very much different with having this kind of elements where now this long range interaction in the particles would matter much more than maybe this local, etc., etc. So this is the time to solution, how it varies with a number of processes really for a fixed total problem size, at the official definition is. Now, when we talk about weak scaling, that is not at all that simple anymore. And hence, students sometimes ask, there could be different factors where just the speed up by adding more and more processors is not a problem, is not possible anymore. Let's say we need more and more memory as well, right? Not only processors, which is sort of an example of the factor NA or N alpha that you see here. So there you would have seen a size that is basically now thinking about the variability of it. So that depending on the more processors you put, there's also more that you see essentially multiplied by this part from this alpha perspective, where it's n to the alpha. It could be quite something, depending now on alpha, that it is positive. Then you basically would say, at some point in time, it's not anymore not good to parallelize it more. That's why it's probably called weak scaling, right? Not very good to do so at some point in time. And the tail off in weak scaling shows then several aspects by keeping the work more and more increasing. That means more and more, and of course, more and more processes with it means more and more communication exchange as well. And as the data remains the same, it's not less data because the problem domain is not the same anymore. We have more data. We keep on communicating more and more and more. And this leads to communication overheads, for instance. And this means at some point in time, we expect with a weak scaling plot also to tail off, because then, some other factors will have a huge influence in this alpha here, where we basically, see more and more of these limits. And here's just the idea that also, of course, the efficiency is a big part of it. Do we really use the course to the degree where we can do it? You see here two good examples. Again, think about no per core we're increasing here with the problem domain size of 1 particles per core. Now, this is important to understand. So in the strong scaling, we had a certain amount of particles and things we changed. That's okay. But we don't change it per core. We change it for the overall problem. Now, what we keep here basically is a little bit the work for the processes, right? We say we do more and more processes, but we keep the number of particles per core. So hence, we keep them loaded. We keep them active, working. And of course, the runtime is different from the amount of particles per run, but you also see then the difference tail off, especially in efficiency. You see 10,000 particles per core are breaking off quite a lot in efficiency after, let's say 450,000 cores, possibly because there's, essentially too much overhead in communication. So the computing is waiting for communication to happen to give me more particle interactions of the surrounding neighbors. And this is sort of the idea moving towards the Gustafson's law idea, that we need basically larger problems for larger numbers of CPUs, where you need to also compute a lot, right? And this is something where then weak scaling shows you where we vary the number of processors. This is of course now something where we have a fixed problem size, but it is per processor. And in the strong scaling, I put it here again for comparison. We want to see how the time to solution varies when we have a total problem size, when there's not work increased per processor when added. And that's why there are two interesting metrics that are very important these days, also often in publications we do to show, right? People want to know what are the weak and strong scaling plots. If you talk about high performance computing, our code scales, HPDB can, okay, show us this. And the same is true for Pepsi, the tree code here. And this is something which I hope all of you have a little bit understood by now. And just to contrast it a bit again from Amdahl's law, the Gustafson's law, where we said more detail is good. Amdahl's law is a bit different and says basically we are hindered by the domination of the serial parts at some point in time. Now, in the ideal situation, it is now a little bit mathematical, of course, saying like we can have this, 1 minus s is just a fancy way of saying the parallelization part of an application, right? The parallelizable part divided by n, and assuming we can have infinite HPC machines, and these machines today that we actually have in the union are really very powerful already. And when we soon have Jupiter and Jülich with exascale, you will see many applications running in that problem. You have maybe more processors, but the application will not scale necessarily much more. And the problem is really the serial parts, which we will have in many areas when we talk about large scale applications still, and that we cannot improve on by just throwing in more processors. By this, you have learned, I think, quite many terminologies which are very relevant for HPC. I mean, again, I think the laws are good. Gustafson's law, so think about a bit, weak scaling. Amdahl's law, the idea of strong scaling, even if you have n processors for the same problem, serial parts in some point in time will catch you. And I/O is actually here and there also often a factor nowadays. So we learned also the speed up term, which is sort of a kind of a fluffy term, if you want, right? We of course want to show speed up, but then please show it with a graph of the scalability, and usually you also want to have the efficiency with it these days. So how much you actually use the system really. And in order to understand this, in previous lecture series and also in previous courses, we had always one lecture performance analysis. I had to skip this year because we're taking on too much new topics and hot topics as, hyperparameter optimization, AI, everybody talks about it. So we have one more lecture on AI. I need to get rid of some of the elements, but if you are really deep into MPI, And I know from the discussion even today with an SME, some of the student groups will actually use performance analysis with an MPI code probably to analyze the code more deeply. And this is something where you have Scalaska, for instance, Vampire. These are all tools in HPC. And in previous recordings, you will find a lecture on it. So for those that are really interested, please go back into the history of the YouTube lectures. Think about there's a performance analysis lecture somewhere that really gives you then an order of understanding that you just don't run and experiment with the code. You also analyze a lot when you talk about this high scaling. So you will see bottlenecks in MPI, not only what problem in the elements we already discussed a little bit in the last practical lecture with non-blocking communication context, for instance, but in generally in MPI, you would say late sender, waiting along in a blocking communication could be not good. So one of the cores is doing nothing, just waiting. This will be all, let's say, shown in the performance analysis tool. So hence it's a key field also in HPC that I cannot bring completely across in this code. And by now, our centers, the supercomputing centers in the Union, offer also 3 days tutorials or 3 days, just lectures on Scalaska, Vampire. Score-P is another one where you can have work all of them together to understand your code better, what you need, because if you scale up to things we have seen, 500,000 cores, then it's not at all to understand all of that anymore by a human. So there's lots of automation in the space to analyze this for you, to understand where your MPI can be much better programmed, where are bottlenecks like IO, and so on. But in a way, that's all really I wanted to leave you on the table today. We could go on to more and more, let's say, terminologies. Many of them will come also alone from the theory aspect. You can imagine when we talk about the physical laws, there's no end to the physical laws we can have. We will actually see many of them in the second part, really, of this course with CFD, computational fluid dynamics, right? When we there talk about different laws in physics, which then inherently have also steer, some of the applications we do in terms, again, of the things now, domain decomposition, how are basically the physics formulas computed over time. Is an optimization process that takes place. Optimization will be also a key term when we talk about deep learning, something I left here a little bit. You would also continue maybe a little bit with this optimization theory, but deep learning will have a little bit of those, and we'll also come back to some of the ideas how then, HPC can be engaged in non-physics. So today I talked a lot about physics, except a few arrays. But the physics code is, of course, that can benefit a lot from HPC and needs it really to show an evolution over time of this simulations. I brought you here a YouTube lecture again, just to have some stress on materials and so on. You see also nice meshes here again, also to motivate the second part of the course later, because now we will, in the next lecture 4, go again to let's say more basic topic, because this is also related to your assignment. OpenMP, shared memory programming, also very important to understand in HPC. And the applications will follow suit then later, reusing basically these fundamentals that we teach here basically at the beginning of the lectures. In the meantime, your projects with industry will, of course, advance. So here and there, I think the team today I met will probably touch MPI. Some others will just use the job scripts to do some parameter studies and understand the differences between CPUs and GPUs. But we have to have some fundamentals first before we go off into all the different applications. What will Razor do with you? Before this, we of course have to talk about deep learning. Hence, after OpenMP, we will move to the world of GPUs. We will understand why deep learning is now on scale with distributed deep learning, a key factor in training large language models, why this has been a big, let's say, hype now. I think everybody of you is well aware of this, that AI is everywhere. So we will talk about this in lecture, let's say 5, 6, 7, before we then turn to CFD and other matters. Hence, we will continue with lecture 4 next week, and talk to you then.